50 years ago I was still a sort of scientist. Today I'm a sort of diplomat. So I'm losing my science, but I'm replacing it by diplomacy sometimes. This gives you an idea that also Asturians are involved at CERN. And these are some of the Asturians, and I think it's not all of them, working in Asturia for CERN. And what surprised me very much when I saw the next photo, these are the Asturians working at CERN. And with how many people are here, because I thought most of you are there. But you see, there are many young people, and again, these are associates or stipends, and to work for 1, 2, or 3 years at CERN gives you really a different experience, yeah, in this international environment. So I think, at least on the photo, they look pretty happy. I mean, after obtaining the PhD, is for more than 50% immediately in the private sector. So we are really educating not only academia, but also for the private sector. This is very important to keep in mind. Okay? And you might also ask, where do they go? Well, you see they go essentially everywhere. Computing, finance, communication, etc., etc. So, and it's not only, and that's another message, not only for physicists, we have increased this program also to include engineers, computer scientists, even administrative students. Yeah? So again, we try to educate and to train as broadly as possible. Now, a few words also on science. Well, today's scientific challenge, at least one of the scientific challenges, to understand the very first moments of our universe after the Big Bang. The universe started as a very hot, tiny spot, then expanding over roughly 14 billion years, up to a size of 10 to the 28 centimeters, where we are today. Now, if you put the development of the universe on a ruler, you see here, is today 10 to the 28 centimeters. That was at the very beginning a very tiny spot of very hot, dense matter. And you can look into the history of the universe with space-based telescopes or with ground-based telescopes. Now, when you do that, you learn a lot about the history of the universe, but you come only as close as roughly 300, 400,000 years to the universe, to the Big Bang. You cannot come closer because the universe in these first 300,000 years was still so hot that all the photons, all the light particles were still absorbed in this hot, in this hot environment, so no information could come out. If you take neutrino telescopes, then you get up to 1 second to the Big Bang, which is, so what are the key questions which the LHC will allow us to address and maybe answer? So we want to understand the state of matter, the properties of matter after the Big Bang, before protons and neutrons, before nuclei, before atoms have been formed. Then the standard model, in the standard model of particle physics, you see here our periodic system of the standard model with 3 families of 2 quarks and 2 leptons each, and the force carriers which exchange the information of the forces between the matter particles. So this is our periodic system of the microcosm, and yesterday I told also the rector at the university, who is a chemist, that I fly with the speed of light, you have no chance to form ground states. So it is important that you know and that you understand the mechanism which gives mass to fundamental particles. This is a basic ingredient to understand why we are existing physically. So we needed a mechanism which gives mass to the elementary particles. And this mechanism with the Higgs particle was one of the candidates, and on the 4th of July we found something which looks like the Higgs particle more and more likely. And this touches everybody's life, because this is, as I repeat again, the basis why we are existing. Yeah? So it's a fundamental. The more I talk about it, the more excited I get, I must say. 100 billion protons. So more than 100 billion protons are flying around, and then if you bring them to collision, these packets, nothing will happen. So what you have to do, you have to squeeze the packets, yeah, like you do in optics. You squeeze them, you increase the density of the protons, and then when you collide the packets, then some of the protons will hit each other. So then you have some colliding photons per packet. This failure triggered us to run the machine only at roughly half the energy. And this is now what we have to redo. We have to redo all the 10,000 connectors. Either we have to redo them completely or to reinforce them, and that takes nearly 2 years in order to do all the rest of the work which we have to do. And this is the way, once everything is installed, and we can run the machine and we can take data. Now again, these are the interconnects again, which are shown here. It's a little bit too much light, so okay. But this shows in more detail here the interconnects. And you have to remember that during the cool down of the LHC, the machine contracts by 80 meters, 80 meters. So 10 meters. It is also one of the coldest places in the universe because we are running the magnets at a temperature of minus 271 Celsius or 1.9 Kelvin, which is colder than outer space. Outer space is 2.7 Kelvin. We do that in order to minimize the ohmic losses in the magnets. At the same time, it's one of the hottest places in the universe because when we collide the two protons, we create temperatures which are much, much hotter than in the center of the sun, because it is the energy concentrated. The energy comes out of the wall plug. Yeah? So you will never get, with the energy out of the wall plug, you will never get to these temperatures. It is the temperature on a minuscule, it's the energy density, that means the energy divided by the area of the proton. And this is very tons, and that was brought in down to 100 meters in one piece. This was one of the heaviest pieces moved, or the heaviest piece moved at LHC. This is the vacuum pipe where the protons are circulating. This is CMS in an open configuration. You afterwards close it again, and the collision point will be here. And a few examples of technology developments for CMS, you see from very large scale technologies to very small ones, like here silicon scale. You have the technology domains at CERN, and here on the left scale you have the application fields, and you see the number of projects we have here. Now when you project it onto the backplane, you see most of it is in medical analysis. So like PET scans, hadron therapy, etc. So here you can use very quickly the technologies we need to develop for society. And I think it's very important to keep in mind that technology is, and it will be more and more, the most precious resource or whatever. No, it's okay. Okay, so I slow down now. Just quickly back to fundamental science. You saw this, this transparency already. It's really that we started the exploration of a new energy frontier with the proton and heavy ion collisions. And you remember these four big questions, these four key questions, and now I'm just going to concentrate for the rest of the few transparencies which I have on the Higgs particle. Again, to remind you that without this beast we would not exist. Well, then, since we are existing, something else would have been there. But this is the basis of our, we do that in order to minimize the ohmic losses in the magnets. At the same time, it's one of the hottest places in the universe, because when the Higgs boson, and these are the leaders of the two collaborations of CMS and of Atlas, and this is very interesting here. We call it the Higgs particle, but there are many more theorists involved in the development of the theory. And on the right-hand side, you see Mr. Higgs, Peter Higgs, and this is Monsieur Aguilar from Belgium. He published more or less at the same time as Peter Higgs a similar paper, together with Mr. Prout. Mr. Prout has passed away, meanwhile, unfortunately. But the funny thing is, they wrote their paper, both wrote their papers in 1964. Mass of the two photons, or in other words, this is from the standard model, so to speak, the snowfall, the snow field, and then the special snowflake is sitting here as a deviation. But it shows you need to measure many, many of these snowflakes in order to be sure that you have found a special snowflake as an accumulation at a certain mass value. It's a boson that we know, but is it a scalar? Because this is another very interesting feature. All matter particles have a spin. all force particles also have a spin, meaning of exploring 95% of the universe. This would be a gigantic leap forward to understand more than the 5%. So my conclusion is that the future is bright in the dark universe, and I hope that the industry is plugging into that. Thank you.